Okay, so moving on to topic 2, solids, liquids, and gases, lesson 2, changes of state. And that's pages 56 to 64 in your textbook. As always, we're going to start with the connected. So if you've ever watched a burning candle, you've seen how the solid wax melts into a liquid. Circle an area in the picture where you see this happening. When the liquid wax cools, it hardens. How is wax hardening similar to liquid water turning to ice? So here is an example of that, of the circle, what you should do in your textbook. And hardening wax turns from liquid to solid. When water freezes, it turns from liquid to solid. Thermal energy and temperature. What are some examples of things changing state? So changing state is not moving to a new state and is instead, obviously, changing from a solid to a liquid to a gas. So this involves a change in thermal energy and temperature. These two terms are related, but not the same. So thermal energy is what's given off because of the change. So the amount of energy, and a lot of the time it's given off by heat. If it's thermal energy, it is given off by heat. And then temperature is, of course, just the temperature of whatever it is you have. So going into more detail, thermal energy is the total kinetic and potential energy of all the particles in an object or substance. Particles have both kinetic and potential energy, and you can increase thermal energy by heating an object. So enough energy can cause a substance to change states. So basically, if you heat an object, it causes the particles to move even more quickly, which causes more thermal energy. So temperature, on the other hand, temperature is the measure of the average kinetic energy of the particles in an object or substance. The faster the particles are moving, the greater their kinetic energy, and the higher the temperature of the substance. So a thermometer measures temperatures in degrees, such as degrees Celsius or degrees Fahrenheit. So we're going to go ahead and look at figure 2 at the integrate with visuals reading check. So in this, we have this picture of the apple cider being heated on the stove. And we're supposed to draw an arrow on figure 2 to show the direction of heat flow, and then label the apple cider's thermal energy as increasing or decreasing. And so because of the heating, it's going to be increasing. And the heat flow is moving around. It's going from, it's basically just swirling around. Changes of state between solid and liquid. Have you ever let a bar of chocolate sit in a car too long on a hot day? If so, you know what it looks like when the chocolate melts. Some of the solid bar changes to a liquid, but not necessarily all of it all at once. And that has to do with melting points and whatnot. Now, freezing, the thermal energy of the liquid water decreases and the water molecules move more slowly. At 0 degrees Celsius, the water molecules begin to become fixed in place, and the liquid water turns to solid ice. So freezing point is simply the temperature at which it changes from liquid to a solid. So it doesn't matter how much of a substance there is, it will always have the same freezing point. So let's do our reading check. What is the difference between melting and freezing? Melting is when a solid changes to a liquid and thermal energy increases, whereas freezing is when liquid changes to a solid and thermal energy decreases. We are going to go ahead and skip the math toolbox for today also. Changes of state between liquid and gas. Why does a pot of hot soup create steam? How does fog form? To answer these questions, you need to look at what happens when changes occur between the liquid and gas states. So for figure 4, we're going to look at that. Examples of vaporization are all around us. We need to label each picture as either boiling, evaporation, or both. So our electric kettle is going to have both. The footprints on a deck is evaporation, and then boiling soup is also both. Evaporation and boiling. So vaporization is the change in state from a liquid to a gas. Vaporization occurs when the particles in a liquid gain enough energy to move independently and away from each other. So very similar to our activity the other day when we were being the particles. So it takes energy for us to walk away from the group, right? It takes energy for us to move. So you have to have that in order for the particles to become an independent entity. So vaporization that takes place both below and at the surface of a liquid is called boiling. And how do we tell that a substance is boiling? And it's normally because it shows that by bubbling. Evaporation and boiling. Boiling point is the temperature at which a liquid boils. As with melting and freezing points, boiling points are characteristic properties and can be used to identify unknown substances. No matter how much of a substance you have, it will boil at the same temperature. Evaporation is vaporization that takes place only on the surface of a liquid. So how is this different from boiling? So boiling occurs both above and below the surface of a liquid at a substance's boiling point. Evaporation occurs only at the surface of a liquid, and it can occur at any temperature. So you should use the information that I just gave to answer the following. Based on the information given, write down the main differences between boiling and evaporation. The effect of pressure. So when you push on an object, you apply pressure to the object. The pressure depends on the force you apply and the area over which you apply the force. Pressure equals force over area. Gas particles constantly collide with one another and with any nearby surfaces. As a result, a gas pushes on these surfaces. The air that surrounds you is constantly applying pressure to you. This pressure, called atmospheric pressure, can affect how easily a liquid changes to a gas. Think about boiling water to make pasta. Atmospheric pressure is acting on the surface of the liquid water. As the water is heated on the stove, the pressure inside of the liquid increases. When the pressure inside of the liquid equals the atmospheric pressure, the liquid boils. So here we should circle the image in which the liquid would require more thermal energy to change to a gas, and then explain how did you determine your answer. So this one is the one that's going to need more energy. So the left-handed image suggests the gas particles are more active and at a higher pressure. The liquid in the left-hand image would require more thermal energy for the pressure within the liquid to equal the pressure of the gas. So in order to make them look the same, that's the one that's going to need more. Condensation. Condensation is the change in state from a gas to a liquid. This is the step of how clouds form. So you can observe condensation by breathing onto a window. When water vapor in the air condenses into tiny liquid droplets. Water vapor is a colorless gas that you cannot see. Okay, so before we move on, let's go ahead and do the academic vocabulary. In orange juice, bits of pulp are suspended in liquid. Explain what you think suspended means. So suspended is going to mean that it's floating or hanging. Bits of pulp are distributed throughout the liquid. And our reading check. What is happening to the water vapor in the air in the prior photograph? And even in this image here. So it is condensing into tiny droplets and forming clouds or fog or steam. In the prior photo, it's forming clouds. In this photo, it's steam. So, changing state from solid to gas. So this is called sublimation, and it occurs when the surface particles of a solid gain enough energy that they can form a gas. During sublimation, particles of a solid do not pass through the liquid state as they form a gas. One example of sublimation occurs with dry ice, which is solid carbon dioxide. At ordinary atmospheric pressures, carbon dioxide cannot exist as a liquid, so instead of melting, solid carbon dioxide changes directly into a gas. Alright, so now we'll do the model it. So dry ice sublimes, or changes directly from a solid to a gas. So think about what is happening to the particles of carbon dioxide as the dry ice changes from solid to gas. Draw models of the particles in the two phases of matter. Use an arrow to show the flow of thermal energy into the solid carbon dioxide. So your image should look something like this. We have the very uniform rows, columns of the dry ice, and then as it turns to gas, it's more free-flowing and moving around. There's more thermal energy. And then the arrow to show the flow of thermal energy into the solid carbon is right down here at the bottom. So that concludes lesson 2. So now it's time to do our lesson 2 check. So what is the main cause of any change of state? And that is gaining or losing thermal energy, which causes a substance to change state. 2. If there is a higher gas pressure above a liquid, what can you say about the amount of thermal energy required for the liquid to change to a gas? And it takes a higher amount of thermal energy for the liquid to change to a gas than if the gas pressure were low. 3. In terms of changes in particle motion and thermal energy, how does condensation differ from evaporation? So during condensation, gas particles lose thermal energy and slow down, which allows them to condense into a liquid. During evaporation, liquid particles gain thermal energy and speed up, causing them to break free of each other. If you left a block of dry ice in a bowl at room temperature all day, what would happen to it? And it simply is going to sublime. All of the dry ice would turn to gas, and the bowl would be empty by the end of the day. Solid substance A has a melting point of 100 degrees Celsius. For each substance, identify its state of matter and describe the motion of particles when the substance. You will not be able to do that because I did not put all of the question there. However, you can do that in your workbook. Alright, so the full question is solid substance A has a melting point of 100 degrees Celsius. Liquid substance B has a freezing point at 110 degrees Celsius. For each substance, identify its state of matter and describe the motion of its particles when the substance is at 115 degrees Celsius. So the answer, solid A would be a liquid at 115 degrees Celsius. Its particles would be moving more quickly than its solid state. Liquid B would remain a liquid at 115 degrees Celsius. Its particles would be moving slowly, but not yet slowly enough to be a solid. And that concludes Lesson 2.